Welcome everybody to MCToon Live. I'm your host, MCToon, and I have a special, different kind of things that I'm doing today than I normally do. Today, I am interviewing with Cody Payne and we are interviewing Ruth Kastner, PhD, who has a paper that we're going to be talking about, some other things. The paper that we will be discussing, I've already linked in the description, and the as well as the link to her website where you can find anything you need on her. Welcome, Cody and Ruth.
Hello.
Thank you. Thanks for the invitation.
So anyway, Ruth, why don't you, so people know who you are, you want to introduce yourself a little bit and give a little background?
Okay, well, I'm a philosopher of physics, and I actually currently live in Idaho. That I do have an affiliation with the University of Maryland Philosophy Department as a research associate there. And I've been researching my main interest is interpreting quantum theory, addressing the measurement problem of quantum theory, which, those of you who are watching are probably familiar with the Schrodinger's cat paradox and those kinds of paradoxes that tell us that quantum theory has a problem. The sort of the standard approach to quantum theory has a problem telling us what counts as a measurement and why we get outcomes. And, we do see outcomes. And the theory has trouble kind of getting to that point of saying, well, something happened. How did something happen? So since about 15 years ago, I really got interested in the transactional interpretation that was developed by John Kramer. And I actually now call it the transactional formulation, since it's really got some different physics going on from the way the conventional theory is set up. So, that's what I've been doing. I've been, researching that, extending that original approach into the relativistic domain. And recently, together with a colleague, Andreas Schlatter, we realized that, in fact, you can get a nice reconciliation of the quantum level with the relativistic level and come up with an approach to quantum gravity. So that's kind of it in a nutshell.
Awesome. And Cody's been on my channel before, but for those who are unfamiliar, maybe Cody, you want to introduce yourself?
Yes, so I'm Cody Payne. I am a PhD student at the University of North Dakota in physics, quantum optics, and I love quantum foundational questions, just like what Ruth works on. I love philosophy of physics, kind of dabble in it on the side when I can. And so when I saw that she had published a quantum gravity paper, I thought, what better way to kind of get her on the channel, get some word out there about some really good science going on, and kind of get the word out and let her speak. So cool. That's why we're here.
All right. Well, I've read the paper, but it's I think Cody has a better grip on it than I do, so I'll let Cody and Ruth talk for the most part here.
Yeah. So Ruth, why don't you kind of start by trying to explain the transactional interpretation, how it kind of fits into the mold of what the problems we're trying to solve in even doing this whole interpretation of quantum mechanics thing, and how it solves those problems in a way that's better in your estimation than, say, Copenhagen or Many Worlds or Pilot Wave or anything like that.
Okay, well, the key element that you get with the transactional formulation is a different way that fields operate. So it's based on what has been historically called the absorber theory, or sometimes called the direct action theory of fields. So this is a kind of an unusual metaphysics, if you will. It's an unusual way of thinking about the way fields behave, but it really does involve a mutual interactive relationship among charges. These are things like electrons, atoms that have electrons as their components, as among their components, and that they are that in fact absorption is playing an active role. So what you get is, under certain circumstances, you get not just an emission, but you get a response of the absorber. And you can quantify the conditions under which this happens. And when you get this response, it's precipitating what we can call a measurement interaction. So, kind of in a nutshell, I mean, you can get more quantitative, and I can tell you what kinds of fields we're dealing with here in this interaction. But kind of the concise version of that is that the fields are considered to be directly sourced by charges. They're not just kind of freestanding, mechanical systems in themselves, which is the way fields are usually thought of in physics. So these call them fields because they are influences in a sense, and they can be quantified. But in the transactional formulation, when you have a measurement interaction, what you're really getting is an active response by absorbers. And together, emitters and absorbers will give rise to this, basically a photon that carries real energy and other conserved properties from the emitter to the absorber. So this is what counts as measurement. And it's non-unitary. So this process means, the term non-unitary means it breaks the deterministic evolution of the Schrodinger equation and so on. And that's kind of considered, it's conventionally thought that in physics, all these processes are always unitary, always deterministic. And that's actually the problem. That's what leads to the measurement problem. So
for instance, I'm so sorry.
Yeah, no, go ahead. Yeah, please.
I was going to say, for instance, like the many worlds interpretation would be an all unitary. There's no collapse. There's no non-unitary element whatsoever. Right.
Yes, exactly.
Okay.
Yeah. Yeah.
Cool. I'll ask Toon, do you have any clarifying questions on?
Yeah. So this is done where there's mass and mass interacting, and the relationship is by one side emitting a photon and the other side absorbing the photon. Is that right?
Well, actually, what you described is really kind of the conventional way of thinking about, how these things happen. In the direct action theory, you really don't have any real photon unless you get a specific kind of absorber response. So there's a lot that's kind of going on behind the scenes at the quantum level. These are processes that are going on that are kind of precursors to what you just described. It's going to culminate in that, what we would call an actualized transaction, would culminate in a photon, a quantum of the electromagnetic field with energy, momentum, and so on, leaving the emitter and being absorbed and actually being received and incorporated into that absorbing system, which is like an atom or molecule. But that's kind of the final scene, if you will, that's filmed. But but before that, we do have a lot of physics going on, and that is so that what Kramer called an offer and a response. So that you have these are fields that are generated by an emitter and say a set of absorbers, but these responses are part of the ingredient that creates that real photon. So they are actually generating the absorbers are generating a field that becomes the ingredient, a component or an aspect to building up that field that ends up being that real photon.
Okay. Let me see if I can clarify that and kind of summarize what you just said. So typically in a standard quantum field theoretic or just classical field theoretic view, we think of, well, in a classical sense, we don't think of a photon, but we think of a photon as kind of existing independently. It's an excitation in the field that's kind of there. But the difference here is in the transactional interpretation, the photon really only has existence insofar as it's facilitating that emitter-absorber interaction. Is that about right?
Yeah, well, it's kind of the culmination of it. I mean, what we call a real photon. Just to get a bit technical, that means it's on shell. So that means it's not a virtual photon. It's real, real measurable, detectable energy. That basically obeys the Einstein relation between energy, momentum, and so on. So these interactions are actually building up that real photon, which is then the culmination of this whole process. So yes, it doesn't exist independently, and it's very much dependent. The real photon is very much dependent on those sources and the way they interact. And when we say source, we mean the absorbing system as well as the emitting system.
Okay. So to my understanding, what you've just described, that's kind of the bare transactional interpretation. That's more or less what John Kramer developed, with maybe a few modifications of your own. Whereas you have gone further and kind of developed this whole ontology of what the offer and confirmation waves correspond to, and kind of the physical consequences of this, the actual ontology of the system. Could you go into that a little bit?
Yeah, I mean, I think I would say that the key step, that I kind of came across or realized, that the missing link between the non-relativistic transactional formulation and a fully relativistic transactional formulation is actually understanding that this quantity called charge, which is, you can technically call it a coupling amplitude. So take an elementary charge like an electron. It has an elementary charge, and that is actually plays an important role as a stepping stone from the purely non-relativistic theory or model here to the relativistic formulation. And that is that this coupling amplitude is actually the amplitude to emit an offer or confirmation.
Okay.
So in other words, at the relativistic level, we don't just have responses. This is the shortcoming, I think, of the classical absorber theory that was pursued by Wheeler and Feynman, as well as the non-relativistic transactional interpretation. It was kind of assumed that absorbers are just, that's what they do. They respond. If you're a charged particle, you respond. But no, in fact, you do not always get a response. And so the relativistic development of the theory is quantifying in large part is to quantify the conditions under which you will get that non-unitary process. So absorbers don't always respond. And when they don't, what you have is a virtual photon connection. So you have, say, these are kind of scattering type interactions, say between two electrons, so that they are exchanging. They are connected by a direct action field, and technically it's the time symmetric propagator in the direct action theory. So they are always connected by that field, but that's the Coulomb field. So that is that's not a measurement. So the relativistic development allows us to articulate, when you're going to have the usual unitary interactions that you need in physics. These are described by a Hamiltonian. You need to be able to say, my system is subject to a Hamiltonian, there are forces going on. These are described by these virtual connections. But then when you want to say, oh, look, I'm going to do a measurement, I'm going to get an outcome, unless you have a non-unitary process, you can never say why you got an outcome. And that is what is triggered by absorber response. So the relativistic development quantifies all that.
Okay.
So go ahead.
Oh, I'm so sorry. I'm not trying to interrupt you at all. Let me maybe ask you, can we kind of peel it back a few steps? For people who don't have a background in physics, are you able to explain this on kind of an elementary level? Maybe just a suggestion, but you can do it however you like. I was thinking, if you take the double slit experiment, which most people are semi-familiar with, could you kind of cash out these concepts in terms of elements of that experiment?
Okay, yeah. I mean, so if you have, say, I guess the one that's truly puzzling is, having an electron going through this two-slit experiment, and if you send them slowly enough, you know, in a very sparse way, so that you probably only have one electron going through this apparatus at a time, and you still end up with this interference pattern, and that's deeply puzzling. So what's going on there is, in fact, yes, electrons are, you know, quantum systems really are wave-like, and what's happening with this electron is it's having unitary, what we call unitary interactions with the slits, so that it's not collapsing at the slit, the one that goes through. I mean, some of them will be just absorbed by, blocked by this, but the ones that get through are interacting in this force-based way with, say, with the slit boundaries, the material in the slit, so the electron really is, I mean, the bottom line is the electron really is wave-like. It's not really a hunk of matter like a little ping pong ball. But in the transactional picture, what really happens when you get at the end, you are going to get a probability distribution for where is this electron going to become part of the detection screen. Well, what actually happens is that the electron has, you know, a quantum state, and it is going to transact with the screen, with this detector screen, and it's going to exchange photons with it, or a photon, say. And so this process is what's going to give you a situation where you're going to get essentially collapse. You're going to get a real photon that really ends up being detected somewhere, that leaves signs that, you know, detectable things, influences you can see. So this is kind of the wave particle duality, is, you know, we have to really accept that these quantum systems are not little localized corpuscles, but that the way we end up getting a result that looks localized is because we really did have this transaction at the end. You know, and you can quantify, well, why is it that I'm going to get essentially collapse of the quantum state, so to speak? You can quantify that in terms of this transactional picture, whereas you really can't in the conventional picture. You have to go, well, everything's just an interaction. You know, so well, now, you could, in the conventional approach, you're just saying, okay, my electron's getting sort of correlated with the slits that it went through. It essentially goes through both of them because it is wave-like.
Yeah.
And then you say, okay, now it's correlated with the detection screen. And now I'm coming in, I'm looking at, now it's correlated with me. So you get these endless correlations and you never get a result. So, but in the transactional picture, you can actually say why something really happened at the screen, and that photon really ended up, you know, being absorbed by the screen.
And that decisive factor is absorption. It is absorbed by the screen.
Yeah, it is a final absorption, right? Yep. Yeah.
So that is where the collapse of the wave function happens, is in that moment of absorption. That's the
right.
That non-unitary interaction, to use the
exactly right. So if you really do get this electron, you know, giving up a photon, a real photon that is then received by one of these pixels in the detector, that is the collapse or reduction of the wave function. And yes, you really got a result, and that's why you see something.
Okay, thank you. So let's so in your opinion, unless it has changed, in your book on this topic, you speak of the offer wave and the confirmation wave, as you call them, what comes from the emitter and what comes from the absorber to facilitate this interaction. You say that what these actually represent is possibility, is an ontological possibility of where you might find an absorption, where an absorption could happen, where a transaction could take place. Have I summarized that correctly, and would you like to elaborate on that?
Yeah, you know, in a sense, I mean, they're forms of existence. So, I mean, I take these things as physically real. You know, obviously, I think atoms are physically real, and electrons and so on. But the reason, and I have to say, you can adopt this transactional formalism without necessarily buying into my suggested ontology, right?
Right.
But the reason I suggest that, that these entities are really kind of potentialities in some sense. I make a distinction between a potentiality and an actuality.
Yeah.
So the reason you kind of need to do that, I think, is because what they are really, when you look at the mathematical structure of these quantum states, these are what's called Hilbert space elements. They're elements of a mathematical space that is multidimensional and complex, meaning it has imaginary components to the amplitudes and so on. And that's not a space-time thing. So for me, it's a matter of consistency. I don't want to say that these are space-time objects, because I just don't think that's consistent. So I think what I've been doing is suggesting let's kind of have an open mind as far as the ontology of the world, and that maybe quantum theory is telling us it's actually kind of bigger than we thought. And I often picture this in terms of an iceberg, where you got the iceberg where just the tip is what we can consider our space-time, appearance level, and that's what I call actualities. But there's all this stuff that's kind of hidden from us for the most part, and I take it as real. I don't take it as some abstract, thing. So it just has a different mode of existence.
And are these some here might be familiar with like the Feynman's path integral formalism, where Feynman talks about how an electron might take every possible path, not just like the straight line path, not just the path through the two slits, but every possible path. In that sense, does your ontology kind of capture that? Would you say that the entire set of offer and confirmation waves, the entire set of the entire set of possible transactions is captured in that same mathematics of the path integral?
Yeah, I think it is. And I mean, the only aspect in which I would sort of differ from that usual way of putting it is that I think that, Feynman wanted to think of it as a little particle. Yep. If you take the position as your determinate observable, then that's the description you get. On the other hand, if you think of these entities as wave-like, then you've naturally got that kind of describes wave behavior. So the mathematics is the same, but I personally think it's more natural to think of it as a wave. And indeed, that's what's described. That describes these offers and confirmations.
Yeah.
Yeah.
And I would tend to agree with you.
Yeah, the thing that's missing, though, in Feynman's picture is that he only has the offer wave.
Yes.
Right. So there's some overpass. So, and that's why, when you look at on my blog, I have a discussion of Feynman's, he has this lovely account of, does a photon or a particle smell all the paths, and how does it know where to go and so on. And then he starts talking about, well, when the experiment is finished, then you do this or that. And what he can't say is, when is it finished? And that's what you don't get your experiment actually finished unless you have, that absorber response.
The absorber,
that's what's missing. Right.
Perfect. Okay. Let's move on and change track to, let's talk about gravity. So part of the reason I brought you on was, in our community, in the so-called the flat Earth debunker community, and Toon is more of the expert than me, but flurfs we call them flurfs. Flat Earthers like to deny the existence of gravity. They say mass does not attract mass, and certain contingents of them will say what's really happening is electromagnetism or electrostatics or some kind of word salad like that. And so when your paper came out and it started kind of getting traction and getting like popular science articles written about it, I expected, and maybe it's happened, I expected the flat earthers to kind of pick up on it and say, look, see, gravity really is electromagnetism. And so part of my motivation was I wanted to kind of debunk that and preempt that. So can we talk about your model of gravity that is kind of comes from the transactional interpretation. But before we do, can you confirm, does mass attract mass, roughly according to Newton's law?
Well, yeah, does Matt, I mean, you know, it's really, I hate to burst your bubble. I mean, it's really, well, yes, mass effectively ends up, we get phenomena that could be described that way. But in fact, I have to say, if those masses didn't have any charge, then you wouldn't have the dynamics that you need in order to get anything to happen. But so it's a very subtle kind of question.
Yeah.
But you know, I have to say, before we get into this, I think the flat earthers are already done for, because they put on their site a while ago, I think it was maybe a couple years ago, the flat earth approach is endorsed all around the globe.
Yeah.
So
we love that.
I can't, you know, I'm not sure how much energy you want to spend on. Yeah, but anyway, yeah, go ahead.
So maybe let me clarify. It's not that mass seems to attract mass because they're actually attracting each other electrostatically. It's that.
But gravitation isn't electrostatic attraction.
Right.
That is correct. You are right about that.
That's what I want to clarify.
Gravitation is not just the Coulomb force. No.
What you mean when you say there wouldn't be no gravity without charge is that this coupling amplitude for matter and an electromagnetic field would not exist if there were not charges. And that's what facilitates. You would get no transactions, and you would get no space-time events. So yes.
Yeah, so we'll just be in quantum land. And
I have a question then. So say you had fully ionized particles, helium, hydrogen, no electrons nearby, right? Just the ions. Now they have charge, but they don't have electrons, so they can't participate in the emitter absorber thing.
Oh yeah, anything with charge can emit and absorb. I mean, it's usually the electrons that are doing that, just because they are the components of atoms and molecules that are kind of available, you know. And you need a bound state. You know, you need like an object that is like, you know, like an atom or molecule, in order to provide these internal energy levels that allow you to have the conditions for which you can engage in a transaction. In other words, you have to be able to satisfy the conservation laws. And for that, in order to have a transactional situation. If you don't have that, then all you have is forces. You have these virtual interactions that are like scattering, but you're never going to get any measurement type interaction. So you need these bound states with structure.
So I'm just right on the edge of handling this. Yeah. So what if, I know that they're unstable, but what if you had a collection of pions or mesons, right? Would they still participate in having mass and causing this interaction?
Well, yes. I mean, under suitable conditions, you can have, sets of charged particles that can have transient bound states. They can form transient bound states if there are any sort of opposite charges involved at all. So you can have transient bound states, and you can have these kinds of conditions under which you could have a transaction. So yes, I mean, it's not a stable situation. It's not like an atom, a hydrogen atom sitting there and having a stable energy structure. But yes, you can, and in fact, this is many times when you have heat-related interactions. These are so-called soft photons, and they're low energy, infrared photons. These are emitted and absorbed in the kind of the larger energy, more diffuse energy levels of an atom or molecule, where there are these higher moments of the field and so on. So it gets a little messy that way, but yes, if you have charged particles, you definitely can have a situation where you can have transactions.
Yeah, cool. let's actually get into kind of the meat of the paper. Do you mind if I try to kind of give my understanding of your model of gravity, your transactional model of gravity, and then you can kind of fill in the details? So essentially, you say, imagine there is a shell of massive particles, and in the middle of that shell, there is an emitter, something that can emit a photon. And the shell of atoms is a set of possible absorbers. So when that photon is emitted, there's an offer wave. There's all these possible absorbers, and there's some entropy associated with that state of possibility, that kind of uncollapsed quantum state. But when a transaction actually takes place, that's associated with a change in that entropy, which is in turn associated to a change in the energy, which is in turn associated to, you can kind of take a work equals FD sort of equation, and then derive from that a force that tends to draw this shell of particles towards the center. Is that about right?
That's pretty much it. Yeah. I mean, I would just say that, this notion of a shell can be defined, whether or not we actually have any masses there. What we do is our model is an idealized situation where we have a very massive, a central mass that is serving as a source of emission. So it's big, capital M, and then we have a so-called test mass that could be anywhere out there and could end up being actualized at any particular radius. So when we're considering, like the possible distances, we consider that entire shell as sort of a set of possible positions for this test mass to be located. So you can kind of think of it as a set of possible positions at that particular radius. And yes, and I mean the key component of this theory is basically a so-called entropic force, which is basically just defined. This is a standard thing in other systems, where if you have a well-defined temperature, ambient temperature, and that can be defined by this source mass for a particular radius. So like how much energy can this thing generate for all the possible absorptions around here? That defines a temperature. It's like an ambient temperature that applies to a particular shell size. And then when this test mass gets actualized at a particular shell, that corresponds to a little bit of a cost of energy at a particular temperature, which is a quantity of entropy. So you get a change of entropy associated with a particular temperature, and that gives you an effective force. We have to remember, for relativistic situations, this force is defined just relative to a particular coordinate frame, and so if we've got our, we're viewing ourselves as in some static frame looking at these masses, then by reference to that frame, this will look like a force that's pulling that's higher. The force is higher, the closer this little test mass is going to get.
Perfect. And from that, you can actually, it's not just a qualitative prediction, you can actually quantitatively derive Newton's law of universal gravitation.
Right. Mm-hmm. Yes.
And actually, we don't need to get into this a whole lot, but just for posterity's sake, you can also take the same model and make certain like relativistically proper assumptions, and also derive Einstein field equations from this.
Exactly. Yes. And I mean, the innovation in our model, this gets a little bit technical, but you can, because the set of space-time events is created through these transactions, and the transactions are being mediated by light. You can define a sort of clock that you can say, well, my systems are going to be participating in a kind of a periodic process. That the period of this process is going to be dictated by the temperature. And this is building on work that other people have done with the so-called notion of thermal time. So with this notion of thermal time, it's like how fast a process is generally going at a particular temperature. And you can define a clock that corresponds to this thermal time. And that is how we end up getting basically a well-known relation between temperature and acceleration that is known in the literature as the Davies-Unruh temperature. And that actually does a lot of heavy lifting in our model. So we actually use that, in a sense, to derive the Einstein equations. And we can also use a form of that to actually get the corrections to Newtonian gravity that you need, to correspond to the so-called dark matter and dark energy. So these corrections seem to naturally come out of our model, without having to be kind of put in by hand.
Yeah. Awesome. I'll let Toon maybe ask some clarifying questions here. If he wants to here. If not, I can move on.
Let's see. I have, I've asked the chat, and chat, if you do have questions, do tag me and I'll forward them. But I don't have any at the moment.
Okay. So I saw a question in the live chat earlier, and after this we'll move on, that speaks about, he mentions that it's a PhD, actually, it's a physicist in the chat, who mentions that it seems like in your derivation of the Einstein field equations, you used a cosmological constant that has the reversed sign of how it's typically used. Is that correct? Did you invert the sign?
I mean, it's a positive cosmological constant.
Okay.
So, yeah, I'm not sure. I hope there wasn't a typo in the paper or something. Yeah. But it's supposed to be the same sign.
I think typos creep into even the most combed over papers.
What might be confusing is that the way the Einstein equations are written in our paper is the so-called trace reversed form.
Yes,
which looks, so maybe but it's equivalent. So that might have caused some confusion.
And I think you just alluded to this a second ago, but can you go into a bit more detail? How does this model it has dark energy and dark matter kind of baked in, those corrections kind of like baked in from the start, or maybe not baked in, maybe that has a implication of like ad hocness, but it kind of naturally comes out. Is that correct? And can you elaborate?
Yeah, I mean, this does get a little bit technical, and it involves making use of an invariance that is kind of hidden in, we would say it's already there in general relativity, and it's just kind of hidden. And what it is, for physicists who are familiar with the Ehrenfest-Tolman relation, basically there's a relation that says that the ratio of the time increment to the thermal time for across different reference frames and different temperatures is the same, is equal. So what this turns into at cosmological scales, I mean, if you're looking at an entire galaxy, then basically what this relation turns into is that the entropy times the temperature of a particular frame, each frame's particular product, as entropy defined relative to that frame and the temperature defined relative to that frame, they're all equal. That's a constant across frames. So if you use this invariance principle, basically ST is invariant. That's what allows you to get an expression for the effective acceleration that an observer is going to see. Once you impose this equivalence, this invariance, you can extract this equation for, what kind of acceleration am I going to see as an observer looking at a galaxy, at a particular part of a galaxy. And when you solve this equation, what you get is the Mond correction. The MOND, you just get that. So it basically just falls right out of this invariance principle.
That is really interesting. Okay, here's maybe the last question I'll ask on this topic, and then we'll move on. Maybe kind of circle back and talk a little bit more about the transactional interpretation. Does this model, besides just being, in my own opinion, like very beautiful, very parsimonious, as far as a derivation of all of these things goes, does it make novel predictions that you could use to test it against, like other models of quantum gravity or so on.
Right. Well, this is the thing, the predictions are our model is empirically equivalent with the conventional approach at the level of the Born probabilities, the quantum probabilities, because it derives the quantum probability law. And so, this people tend to really want a novel prediction. So what and I say, no, it's not going to be distinguished empirically in the sense of, we're going to tell you that the Born rule has to be changed, and now you can test. It doesn't have that kind of thing. But what makes it a powerful theory, I think, is that there are anomalies with the conventional theory. So the measurement problem is an anomaly. The rotations of galaxies is an anomaly for the cosmology that's based on that conventional approach. And so there are all these anomalies in physics, and there are others as well, that this approach just solves all these anomalies kind of that seem to be coming up in different disparate areas of physics. So in that sense, I kind of see it as analogous to, back when before relativity, you had Newton's laws having a bit of trouble with the perihelion of Mercury, that it had this precession. And the Newtonian model could not explain that. Well, Einstein, developed relativity, and that resolved that existing anomaly. So this is what the model does, and then it resolves existing anomalies. And then the other thing I would say, okay, the novel prediction is you will get a measurement result. That's one way of looking at it. I mean, it's an anomaly, yes, but our theory predicts that you will get measurement results, and it will tell you exactly what you need to do to conduct a measurement, something that can be called a measurement, and it will tell you when your experiment's finished.
Right.
So it answers all those questions.
You could almost think of it as like a quirk of history, that if we'd found the transactional interpretation first, we might have predicted gravity. But just as a quirk of history, we happened to discover gravity first. And so
sure. Yeah. And I mean, along those lines, I mean, if, when Wheeler and Feynman were investigating the absorber theory, the direct action theory, for kind of different reasons, they were trying to eliminate self-action because they thought that it led to energy infinities, which it actually doesn't. But that they were interested in it. If they had stayed with it, then we may have ended up solving the measurement problem decades ago.
That's a really cool thought, like just the all the what ifs of history. Perfect. I have a question that goes right along with this, although it does change track just a little bit. So this is a framework that seeks to derive general relativity. Most philosophers of physics and most physicists, I would say, look at general relativity and derive from it like the block universe, the B theory of time. But from reading your work, and again, unless you've changed this, you are an A theorist of time, and the transactional interpretation is kind of fundamentally an A theory framework. Is that right?
Well, yeah, in a sense. I mean, like, I don't buy McTaggart's categorization in the first place, so I would, I think there is genuine becoming. So if that's what we mean by A series, that there is genuine becoming in the sense of a space-time construct. I mean, what I have to note, with McTaggart calling something the B series is he presupposed a block world. And that's what's not commonly noticed. He just said, well, in defining my B series, I'm just going to assume there is a block world. And people don't notice that. I'm like, wait a minute, why should events have this relation that you're ascribing to them for the B series unless there were a block world already? Because if there isn't a block world, there's no B series.
And so to maybe clarify people who don't understand this distinction, the B theory of time says that all moments of time are equally real. Like there is no past, present, future. Our consciousness kind of just moves between different time slices of the universe, so to speak, different moments of time. Whereas the A theory of time says there really is a present that objectively exists, and it actually is moving in some sense. There is an arrow that is objective. It isn't just kind of an artifact of entropy. There is genuine becoming, and that would be your view.
Right. And of course, I mean, the thing about, McTaggart's proof is, I don't mean to get off on McTaggart, but the thing about it is like you cannot set up his alleged proof that time is meaningless or that time is inconsistent and there's no real time. He gets by assuming the existence of a block world. So it's circular. It's circular. It's completely circular. He assumes there's a block world, and he says, well, but then some people might think that there's becoming, and so, but because I decreed that there's a block world, there can't really be any become. It's completely circular. So I'm kind of like, my eyes are bugging out, like, why did anyone take this seriously?
Yeah.
So that's my next paper is like, why did we ever listen to McTaggart because his proof is circular? But that's a different topic.
I look forward to that. Maybe we could even have another discussion about that.
That's a different topic. Yeah. But yes, I think that there is. I mean, I guess what I would just say is the usual thought about what the A series is kind of thought of as a moving now, like the now is moving, but there still presupposes some background space-time diagram that I'm moving through, and that's part of the. That's part of the misconception. So what I'm saying is now is just, that's the base of what we call now. The present is where everything is, certainly quantum mechanically. You can call it the eternal now if you want, And it sounds poetic, but really, literally, physically, we don't move anywhere. We're always now. What's moving is stuff's falling away from the now. So that's the arrow of time. Stuff's falling away, so something's happening. There's a flow in a sense, but it's not like we're moving along a space-time diagram in some future direction.
In your model, it is the transactions that take place in what you call pre-space-time. Like space-time isn't there yet. What's really there is, in some sense, this higher dimensional Hilbert space, and the actualized transaction is what kind of stitches together each moment of time to the next. Is that about right?
Right. Yeah. And I would say that, that notion of time, which is part of the structure of this space-time construct, is kind of, it's a metrical notion of time. So that it's defined relative to some frame and so on, and covariant way, in a consistently covariant way. Right. But at the same time, there's a kind of a time clock that you can see as applying to the quantum level. And really, it's a kind of, it corresponds to proper time, in a sense, in the relativistic framework. So there's sort of a proper time, and then there's a coordinate-dependent metrical time.
So I think what people might get confused about listening to this is people look at relativity, and they say, you have the relativity of simultaneity. Like a present for me might not be present for someone in the Entropic galaxy. There's like transformations that you can do that change present according to who, simultaneous according to who. So if there's not, according to relativity, it seems like there's not that objective now that you speak about. So whose now is that objective now, or how do you kind of reconcile that?
Well, it's really, the notion of now is really properly understood as a local one. So when we get into trouble is when we say, okay, my now is right now. I'm looking at my clock, and I'm going to draw a line of simultaneity. And all you've done is you have designated a map. You have just simply created a map and drew lines on a map. So what you call, it's not so much now, it's what you call t equals 0. If you want to call it t equals 0, but your now is going to keep, then it's not going to be t equals 0 anymore. So it's the time index that's relevant. The time index simply applies to a map. So the mistake is saying that the numbers I put on my map should apply to someone else who's, space-like separated from me, which means that, I can't send a light signal to them and still be at the same point on my map, But
each of us, like Alice and Bob, would both agree there is a present. And they wouldn't necessarily agree, but if they could see the whole kind of framework of reality, they would agree there is this becoming. There is this objective becoming. They just might not agree of kind of
what time index to give it.
Exactly. Yeah.
Well, that's really it. So what we have to do is distinguish between the notion of the present and a time index. They're not the same thing.
That
right.
makes sense.
Yeah. I mean, and it's commonly thought, there's this argument called chronogeometrical fatalism that people claim that is implied by relativity. And you mentioned that earlier. And it actually isn't. That's a fallacy. And other authors have noted, Raphael Zorkin and his colleagues have also noted that if the events of space-time, if they're, where space-time events are being so-called sprinkled in, that the new events are occurring, if they're being added in this Poissonian manner, which is a specific kind of a probability, if they're added in a specific way that's Poissonian, which corresponds to decay rates and things like that elsewhere in physics, then in fact there's no preferred frame and there's no sense in which there has to be the future already existing. So it's kind of something that people fell into that was not really critically examined.
Okay, that's really interesting, actually. If you could honestly email me some papers on that, I'd love to read them.
Sure.
So what I think maybe a good use of the next few minutes is, before I believe you need to go, before too terribly long, is if there's any questions from the audience that Toon could bring us, and just generally just bring us down to earth a little bit if you want to, and I'll take a little bit of back seat and let Toon take over for a minute.
Yeah, I've got some questions from the audience here. We got Astrocate Sathics says, kind of like what I was asking about pions and mesons. If charged particles effectively create gravity, why are neutrinos affected by gravity?
Well, yeah, I mean, neutrinos have very, it's currently thought they have non-vanishing mass. We don't actually know that for sure, but the way neutrinos would participate in gravity is by way of the weak interaction. So there's still a component of transactions. It's sort of indirect, but say whenever you have, they say, the weak decay of a neutron into a neutrino and a proton and so on, this is going to be detectable by way of a transaction that is mediated directly by the charged particles involved. But the neutrino is crucially part of that interaction, and it influences it. So the momentum of the neutrino and all of its conserved quantities are going to influence that transaction. So, yeah, and of course you can very indirectly, very rarely detect neutrinos and so on. So they are participating. The fact that they can participate in transactions, and they do, is how they end up playing into that gravitational structure.
All right. There you go, Astrocate. Addicted to Globing says, I'm doing my best to understand. Can these transactions be artificially created, as in artificial gravity?
Well, good question. I don't know. I mean, all you need is a bunch of suitable charged particles that are, interacting, but then you've got real gravity. So I'm not sure what would be artificial about it, in a sense. You just, every time you have a transaction, you are establishing basically two space-time events: the emission event, the absorption event, and then that link between them, which is the transferred photon. So that's probably going to be real gravity. So yeah.
Okay. So it's real. Okay. This goes to the Coldplay meme over the weekend. Did the astronomer CEO prove superposition by being in two places at once until observed?
Well, transactions are going to happen at levels of complexity way below hunks of matter like complex systems like us. So it's very unlikely that any particular scientist would be in a quantum superposition. The probability is not zero, but you'd probably have to wait, 10 universe lifetimes to ever see it. So
there's some background to that. It was the CEO of the company Astronomer. Is that right? Who was
yeah.
at a Coldplay concert with somebody that wasn't his wife. The superposition.
That would have been convenient, but no, yes. I really don't think that's credible. So they'll have to come up with some other excuse.
All right. A North Beach says, are there actual entities with mass creating the effects we call dark matter? Or does this interpretation allow us to have the effect out of math without massive particles?
Yes, you get the behaviors of the galaxies that are, the outer parts of galaxies rotating faster than Newtonian gravity predicts. You get that right out of our theory by this subtle kind of form of invariance that I mentioned earlier. So you don't need any dark matter. It's interesting. I was at the Como School in Italy the previous month, and it was a gathering of folks who were looking at this very question. Is there dark matter? Should we be trying to find this dark matter? That if we had more mass in here, then we could use Newton's laws to explain that. And there are kind of two main groups here: the people who say yes, there's dark matter, and the people who say no, the theory is different. Which is, we are sort of among those groups. And it was kind of like being at an epic Klingon battle between the House of Monda and the House of, Lambda CDM, which is the cold dark matter group. And it was quite exciting. But no, I don't think we need dark matter.
Right. The Canadian Space Advocate says, does this model predict gravitational lensing?
Yes, it should in principle. In fact, the other nice thing about being at this conference was that there are some postdocs who are doing really interesting work, and one young lady is modeling gravitational lensing. Her group works on both observing, doing imaging of existing lensing systems, and she's also modeling theoretical predictions for lensing, and she's looking into modeling our theory. So yes, definitely you should get some lensing effects, and we can find out more about them hopefully as this goes forward.
All right. Curious UK Debunks has asked twice similar question. How close are we to solving the vacuum catastrophe? And then, does this have a potential to QFT solving the vacuum catastrophe?
Yes, definitely. There's no vacuum catastrophe here, because that in fact is an example of this approach, this transactional formulation solving several different problems at once. There's no infinite vacuum energy, period, in the transactional formulation. So when you get self-action, it's not energy. It's not, on-shell energy. It's more like self-force. It's sort of force that is not acting over a distance. So you don't get a huge, crazy anomalous prediction of huge vacuum energy. And then you also get, but yet you get a very subtle vacuum energy corresponding to the cosmological constant effect that we observe. And yes, we get all that out of our model. So this problem is solved, and we're just waiting for people to notice that it is.
All right. Clive Wells, another PhD here, says, does her theory have naked singularities? If so, what comes out of the singularities?
Our theory doesn't really predict anything specific about the types of singularities you would have. I mean, it's basically just general relativity with a naturally occurring cosmological constant. And then, to be frank, we haven't investigated, specifically, does this imply anything new about, what kind of singularities we might have? But, you can have black holes, you can have all of the standard kinds of singularity effects that we would have in standard general relativity.
All right. In Town says, how does the holographic principle relate to the emergence of gravitational force?
Yeah, that's a really big question. You know, the holographic principle is really kind of a way of recognizing that that masses, strictly speaking, are not contained in the space-time construct, and that what you need to be looking at is the effect of those masses on a particular shell. So that's just an accurate way of quantifying that fact, and it's you know, I don't really have time to go into, you know, all the details of that, but I do have a discussion of the holographic principle on my blog, transactionalinterpretation.org, and I have a kind of a hopefully user-friendly directed for the layperson that discusses the holographic principle and the how to understand it. But strictly speaking, even in standard general relativity, matter sources of the gravitational field are not in the field. And that means they are literally not in the space-time metric. That's standard general relativity. And people have a hard time with that because they think of space-time as a container. And the holographic principle is just basically enforcing that, no, really, these masses are not in a volume. You know, it's not like you can have a ball here and then go in and see, the mass that's actually giving rise to the phenomena that you see. You're always actually seeing shells. So it's kind of startling, but rigorously speaking, it's really true.
All right. I think I've got one more here from Kango44. In your model, where does the Higgs boson come into play?
Well, I'm not sure we even need the Higgs boson in our model. That is something I haven't looked at in detail. But in the standard way of formulating these theories, you want to say that that systems don't actually have rest mass, because if you assume that, then you don't satisfy a certain kind of invariance that is considered to gauge invariance. But that's kind of an imposed condition, and it's thought that if you let go of that, then you might have various problems. But there are people who have kind of pushed back on that and questioned that. So our model, and to be honest, we have not investigated that in detail, but in our model, we may not actually need the Higgs boson. But this is something that I'm going to look into in the future.
Because we've discovered something at that mass, right?
Right. I mean, and again, discoveries, do need to be corroborated, and I don't want to say no, we didn't discover it. We may have. There may be good evidence for that, right? But we often, there's it's kind of been demonstrated. There's often a bias there where people find the things that they hope to find. So I don't know. I don't want to come down hard on that either way. Okay. But it's certainly compatible with our model. Like, our model is not somehow inconsistent with the existence of the Higgs boson. It just, at this point that we've developed it, it doesn't seem to require that.
Okay. All right. That's what I've got from the audience.
Do you have any other questions too?
I'm good.
Okay. I think I've asked all the questions
for me, yeah.
I had in the main body, and I think we're just about at time. Like, we're just about perfect. So Ruth, thank you again so much for coming on. It has been so nice to meet you and chat with you, and hope to kind of follow up and maybe have another chat like this sometime in the future.
Absolutely. Yes. Thank you so much. It's been really fun to discuss these things. So
yes,
maybe till next time.
So I put your website and the transactional, the one you just mentioned, though. Mm-hmm. Your blog. Transactionalinterpretation.org.
And then there's my author site. I don't know if it's ruthekastner.org. That's my author site. That just has information about my books.
Yep, so, I've got both of them in the description, as well as the link to the paper that we were discussing. So if anybody's curious, they can find it there. And Cody and
Very
I we're going to chat a little bit after, but thank you so much for joining us, Ruth.
Okay, it's a pleasure. Thank you.
Yes.
Thank you.
Have a great day.
Till next time. Thanks.
Yep. Till next time. Bye.
Bye-bye.
All right.
That was fun.
Well, yes. Definitely a I read the paper and struggled a bit to really get it because yeah, it's pretty involved and
I believe you mentioned the book earlier. Maybe not. She has a book called Exploring Our Unseen Reality that I believe she kind of goes over the transactional interpretation on more of a popular level. If anyone's interested in checking that out, and I'm sure her blog is a great place to go if anyone wants to kind of learn more. And anyone with a mathematical background will, I think, enjoy her her primary book on the subject, which is just the transactional interpretation, the reality of possibility. So,
okay. Sorry,
definitely
my
worth
wife
checking
my wife poked in for a second there.
Oh, you're fine.
So cool. I got a couple things that were a little more laddie centric. Itorius
Okay, cool.
says, now we all know how flirts feel when we talk math and science at them. It's also fun listening to smarties talk way above our own level and try to make sense out of it. Learning is fun.
Yeah, Ruth is the real smarty. I'm just learning, but just trying to take it in.
Scoundrel, who is an escapee, says it's flat.
Oh,
Looks like I'm taking that as
not, though.
sarcasm. Janusz Takas says electromagnetic gravity 5-volt battery could substitute for a helium balloon. And of course, yeah, the proposed from the flatties where they say that there's some vertical gradient of it's basically Coulomb's law, right?
yeah, exactly.
Field where there's positive at the top and negative at the bottom. Like, yes, if you rubbed anything on a cat, it would float up because that would give it a negative charge.
Exactly.
So,
what was I about to say? Oh yeah. So we didn't get to it, but if you read the paper, of course, mass comes into all of the equations via equals mc squared. So that's kind of where the reason that mass is involved, the reason why mass matters, is because of equals mc squared, which I think is very cool.
well, yeah, and
But of course, mass attracts mass.
And it does also include the she mentioned it but didn't make it super clear, the photon that is emitted and absorbed is the Einstein Planck equation, E equals
Oh yes, yep, equals HF.
HF, yeah. I posted that in the chat for people as she mentioned that, but I didn't.
Yep. I'm pretty sure at some point, I'd have to read through it again, but I'm pretty sure at some point they explicitly said HF equals MC squared and do derivations based on that.
Yeah. Trying to fix the scene here. Here we go. There we go. Anyway, I think that's about it.
Yeah, that's about it, I think. Unless you had anything else to think about.
I got another live stream coming out tonight later. It's a call-in show for anybody named Mike.
For anyone named Mike, okay. I guess I can't call in then.
It's okay. Just change your name to Mike and you'll be fine.
Okay.
Kango 44 says sometimes this channel is tricky with so many nutters around. Coming halfway through and listening to Ruth, it's hard to distinguish. Is it woo or actually a new interesting theory grounded in reality?
It's definitely grounded in reality. It's definitely like solid physics, legitimate. It's not woo. That doesn't necessarily mean it's true, but it is not. It's not nonsense.
So it's the paper that she has, for example. It's a proposal. It's a hypothesis.
Yeah.
Right.
Yes, exactly.
And which is sometimes is missed by people. You have the hypothetical physics or theoretical physics, right? Here's what we think could be the issue, could be an explanation, and a bunch of these proposed explanations are proposed. And then you have the experimental physics that goes and tests those things to see which ones match reality.
Right. And just to be clear, it is the paper is published in a peer-reviewed journal, like a well-respected journal. So that's a good place to kind of start your search if you're wondering, is this woo, or is this or is this something worth taking seriously? It is a respected physics journal.
All right. Well, that's what I got. People be looking for future live streams. We'll see y'all later.
Yep, sounds good. See ya. Bye.